I would love to talk a little bit about possibilities of generative AI in public health. I think there are some. But I think when you think about the pandemic, at least, the more classic usages would have been forecasting as the dominant one. But there's also some other very interesting ones, like maybe retrospectively trying to figure out where was the first case or trying to reconstruct transmission networks. Classification can be another one.
From PHI Media, I'm Gordon Thane, and this is AI and Public Health, episode 238, Machine Learning and Natural Language Processing. You're listening to the Public Health Insight Podcast, your go-to space for all things public health and global health, from the Sustainable Development Goals to the social determinants of health, as well as interesting dialogues about the diverse career opportunities that exist in these fields. Remember to subscribe to the podcast and leave us a rating on Apple Podcasts and Spotify so other people like you can benefit from our content. Machine learning, natural language processing, rule-based systems, neural networks, deep learning, these are all terms used in the artificial intelligence space. But what does it all mean? Dr. Serina Chang is someone who knows a thing or two about this AI stuff. She's an expert in computational health. She recently completed her PhD at Stanford University and will be an incoming assistant professor at UC Berkeley starting in 2025. Her work has been featured in more news outlets than you can count, including some big ones like the Washington Post and New York Times. The goal of this part of our conversation is simple: to help us understand the basics of AI, as well as some key concepts to lay the foundational knowledge required to apply various tools in computer science to understand the context of public and population health. Let's dive straight into it. And this next part of our conversation will focus on what does computer science have to do with public health. Obviously, I think you've made it clear that there is a way to connect computer science to social sciences, and public health has a huge social science component. So I think we kind of started to build the case for that already, but that's the space that we'll live in for a while. For the person that's sort of introducing themselves to AI and all these lots of different terms and lots of different tools that enable AI to be used for different things, I want to get back to some basics here and help us make sense of all of this. So the first thing is, AI. What is AI? Because AI is a term that I sometimes see being used for when something is automated, as an example, then it's AI, but that maybe doesn't really give AI enough credit, perhaps. So maybe let's define it in the world that you exist in for what we're talking about.
Sure. Yeah. I mean, I think you probably see that AI is so hard to define because I think it is quite broad. I mean, what it stands for is artificial intelligence. And so it really captures anything that falls under teaching machines, teaching computers to simulate or emulate human intelligence. I think that is the definition that I would go with. I think terms like AI and machine learning are often conflated. The way that I would distinguish the two is I think machine learning is a subfield of AI. So it's one type of AI along with other types of AI. So machine learning is specifically trying to learn patterns from historical data. I think that is how I would summarize machine learning. So that still includes a lot of different things. So for example, trying to learn patterns from historical data, that could include, for example, forecasting. Like maybe you tell me COVID cases for every day from the last year, then machine learning could be trying to predict COVID cases for the next week, for example. So forecasting and prediction are common machine learning tasks. Another one is classification. And so that's, for example, maybe you show me lots of different pictures and you want me to tell you which one is a cat, which one is a dog. That's a sort of classic machine learning task where you give me often in like what's called a supervised setting. So maybe you show me what's called a training data set where you have like 500 cat images, 500 dog images, and they've been labeled as cat and dog. And then the machine is supposed to take in those labels as well as the images to learn the patterns, right? To be able to say, that's a cat, that's a dog. And then you show on new images that don't have labels, you show the machine can still predict accurately which one's a cat versus a dog. And so that's called classification, where you have some sort of class. You have like cat and dog would be two classes. You can also have multiple classes like cat, dog, horse, cow, mouse, etc. And that's basically saying, give me some piece of data and I'm going to categorize it into one of these classes. So far we've talked about forecasting and classification. These are two different sort of machine learning tasks, and they're all about extracting patterns from data so we can say something about it on new unseen data. And that falls under AI, but other things that fall under AI don't have to be so data driven. And so AI also consists of, for example, like reasoning and problem solving. And this can even be rule based. Like it doesn't even have to be about learning from data. AI could even consist of, if I wrote down, for example, a chatbot and I just had rules to describe the chatbot. Like if the user says hi, say hi back. If the user says bye, say bye back. If the user doesn't say anything, prompt them with, what are you interested in? Or whatever. Like, you see what I'm saying? That would count as AI, but at least in my book would not count as machine learning. So that's a sort of rule-based version where you are trying to emulate some sort of human intelligence, right? You're trying to talk to an individual, but it doesn't require learning from historical data and making predictions on future data. It's more like principles based. It's like, I understand how interaction should go, and so I'm going to tell the machine how to do that. So yeah, that's another example of AI that is not machine learning, but it's under AI. So hopefully that helps a bit.
On the example, the example that you gave about machine learning, the 500 cats and dogs as an example, if you were to go to 1,000 cats and dogs and images of cats and dogs instead, is that in an attempt to make the machine learning more precise? And because there's a category way of it, and then there's a specificity or accuracy, and that's achieved through more training with more. Am I making stuff up here, or am I on?
Yeah.
Okay.
No, that's how it works? That's right. So if you're in the sort of setup where you have what's called the training data, and that's what the machine gets to see, where it has both the images as well as the labels, you can often improve performance by making the training data bigger and bigger. There are often ceilings to that. So sometimes what you'll do is, as you're training your model, you can plot its accuracy as you add more and more data. And usually the kind of curve that you're going to see is it goes up steeply at first, but it might plateau after some time. And so for a machine learning practitioner, that's quite helpful to plot that curve, because then you can say, oh, well, more data actually wouldn't have helped me. My model has basically maxed out on its ability to predict.
I think that was a very good description of machine learning. I don't know if I haven't researched it enough, but I found that to be a very clear example. And I'm already starting to think through maybe what's machine learning and what's not based on how you define it, which I think is really cool. Now, if we take, you kind of gave some example, AI at a higher level, and then the different subsets. The other term I hear go around, and I think you've used it in this episode too, is natural language models natural language processing. Where does that fit in sort of is that a distinct area separate from machine learning and like more rule-based AI kind of interfaces?
So if you wanted to put it into the sort of Venn diagram, I would put natural language processing as a sub area of AI for sure. And so it definitely falls under human intelligence, or trying to emulate human intelligence. In practice, it is often dominated by machine learning these days. There used to be more sort of statistical or rule-based techniques, but in the last decade, I mean, as many things have been, it's become dominated by machine learning, and specifically a sub-area of machine learning called deep learning, which is basically where you use neural networks and instead of statistical. So maybe we shouldn't get into neural networks.
No, I'm curious. Yeah. So I've heard, so machine learning, then I've heard the term deep machine learning or deep learning.
Yeah.
Yeah. So I think you were going to get, I'm curious if you could explain.
Okay.
Yeah.
Yeah. Okay. So deep learning is, so the tree is the ordering is, we had AI on top, right? And then nested in that is machine learning. And then nested in machine learning is deep learning. So deep learning is a type of machine learning where the model that you're using is essentially a neural network. And a neural network is, the reason it's called a neural network is it sort of simulates a human brain in terms of having neurons. And the way that it typically works is that you have this, a bunch of individual neurons, and they're usually connected through neural layers. And so the simplest type of layer is just like a linear layer. So you're saying, for example, just like a linear combination of the different neurons, and you apply a linear layer to it. So you apply a linear combination to the neural layers, and then it usually goes through some sort of non-linear activation. So like a sigmoid function or a sigmoid function basically squeezes things between zeros and ones. So it takes any real number and it squeezes it between zeros and ones. So that's the sort of, if you open the box, that's the architecture. From a high level, the point of neural networks is that you can take these neurons and arrange them in some sort of architecture. You can stack as many layers as you want. Like oftentimes these will go into hundreds, thousands of layers. And it's a really flexible architecture, meaning that it can capture any function under the sun. And so if you have some sort of input data and that maps to the output label, so in the classification space, let's say that's either cat or dog, the input space is like the pixels of the image. It can be a pretty complex function to map the pixels of the image to the output of like cat or dog. And neural networks are able to capture any sort of function. And so that's one power of neural networks, which is that they're very expressive. They can capture all of these different kinds of functions. Another power of neural networks is that they don't require what's called feature engineering. And so in more traditional machine learning, you would often have to, because the models weren't that sophisticated yet, the machine learning researcher would have to define features for the machine to pay attention to. And so instead of just giving the raw image so let's say we're in the cat and dog example again, instead of only just giving the raw image to the machine, they might have to do some pre-processing themselves. So they might have to like try to figure out, like it's 50% green and like 30% red or whatever, or like it looks like they might have to do the pre-processing of like segmenting the image and maybe even object recognition on different parts of the image. The power of neural networks is you don't have to do that pre-processing anymore. You can just give the raw image to the model, and the model, through all of its neurons and activation, is going to figure it out itself. Wow. And so that's what's really powerful about it. It can both capture these functions, but also it takes away like work that you have to do, where you have to come up with these feature sets yourself, and they can figure it out from the raw data. Wow. And so this is not just for images. This also appears a lot for text. And that's where we enter the natural language processing space. Like if your input data is language, so either text or speech, that would fall under natural language processing. And this can also appear for, other types. Like I mentioned, graph machine learning is a whole sub area. So the input data can also be a graph or a network. And you can develop neural networks for those, which are called, GNNs, graph neural networks.
Does that in any way capture how commonly known tools like ChatGPT works? Is there like a sort of a neural network happening where but it's a text-based platform, so it's doing what you described, not for images but text? And is that kind of, would I be right in saying that?
Yeah. So wow. ChatGPT is a natural language processing model. It is a neural network. It's a very, very fancy neural network trained on tons and tons of data. Another thing that's quite cool about ChatGPT is it's self-supervised. So what self-supervised means is when you're training on, tons of data from the internet, you don't have time for somebody to go through that data and actually give you labels. Like you can't look at the text and have someone go in and say like, here they are trying to say this, and like here they are angry, and here whatever. Like you don't have time to gather all these manual annotations. Instead, what ChatGPT does is it's self-supervised, meaning it takes the raw data and turns it into like the objective that it's training on is in the data itself. And specifically what it's trying to do is next token prediction. So what it's doing is it's seeing the sentence up to some midpoint in the sentence, and then it's predicting the next word in the sentence. And it's doing this over, terabytes of internet data. And by doing this, you can actually learn some pretty valuable stuff beyond just next token prediction. It's learning sentence structure. It's learning social meaning. Although there's also a lot of issues with the kinds of things that it's learning from the internet, as you can imagine, because the internet self-selects for certain types of things. And for example, stereotypes and biases and more toxic language. So there are also these concerns from this completely self-supervised regime, but you can definitely process a lot more data than you would be able to if you actually had to go in and manually annotate every single piece of text.
Then how does this vast technological possibilities that we're talking about connect to population health? Like, how can public health as a field use or benefit from the use of or availability of these tools, these different models, these different concepts to make decisions in public health for the betterment of the populations that are being served? Like that's I guess that's the overarching question there. I did see you did a talk where you talked about recommender systems too. That was very interesting to me. And I think that in terms of how polarization can happen and even the vax and anti-vax kind of, I'm sure, I would imagine that kind of maybe played a role in there too. But I'll take a step back to my question and we'll kind of see where it takes us. How do we use these tools?
Yeah, I think, so let me give you a few examples. I think let's go back to forecasting. So before I was saying a classic example of how AI might be used for public health is, let's say you have case counts, maybe for COVID, maybe for any other disease. You have it for the last year or even for the last several years. You can develop machine learning models now to forecast into the future, maybe the next month, maybe the next week or so, how many cases are there going to be. So that's a very like textbook example of how AI and machine learning specifically might be able to help.
Just a quick, was that just to give listeners an understanding of maybe when these tools are used and how new they are? Is this something that was being used during COVID more broadly by different public health agencies and when they're modeling and when they're doing predictions about case counts and that's winter, and are these the actual tools that they were using to make those predictions too?
Yeah.
Okay.
Yeah.
So it's being used in the real world right now.
Yeah, I think machine learning models. I think I would not think of. So I think the thing that's really taken the world by storm lately is generative AI. So ChatGPT being an example of that. I haven't defined that one yet, but generative AI is basically another form of AI that instead of giving labels to things, so before I was saying, well, you have like the cat dog example, instead of giving labels to things, it's actually generating things themselves. So instead of giving labels to an image, it's actually coming up with an image, or it's actually coming up with some text so that you can have a conversation with it. And so that's really quite unusual. I think, so generative AI, I think there were fewer uses of it during the pandemic, although I would love to talk a little bit about possibilities of generative AI in public health. I think there are some. But I think when you think about the pandemic, at least, the more classic usages would have been forecasting as the dominant one. But there's also some other very interesting ones, like maybe retrospectively trying to figure out where was the first case, or how trying to reconstruct transmission networks. Classification can be another one. So I think under classification, anomaly detection is a common public health problem. And so let's say you have different streams of data coming in, like one of them is like maybe you have case counts from every county in your state, and you're like a state level public health department, and you see all of the numbers coming in. You might see the cases spike for one county. Sometimes that's just due to noise in the data reporting, like maybe they were backlogged. They didn't report over the weekends or something, and then suddenly on Monday, you suddenly have a spike. So trying to understand whether that spike is meaningful or not, you can use machine learning algorithms to try to process maybe all of the data streams from all of the counties at the same time. And maybe if you see 5 counties spiking at the same time, that's much better evidence of a real outbreak happening, as opposed to just a single spike on a Monday from one county. So that's another place I think that machine learning can help, which is processing all of these different complex data sources and compiling them together to figure out the ground truth of what is actually happening on the ground.
And how does it incorporate context in shaping our understanding of what's happening? That's the part that I kind of struggled to understand. If it's a human in a supervisory way coming in and trying to add context, or can machine learning also help us with that?
Yeah, so I think context is interesting. And actually, that actually starts to get into sort of where my focus in the pandemic was. And so maybe I actually paused in my story for a bit where I was saying like, oh, I do social science, but then I started my PhD and we started doing COVID work. So I've always been very interested in humans. And what I discovered was during this pandemic, there is this huge behavioral component to public health. And that's really the component that I was focused on. And so when I say I do public health, it's really this intersection of public health and social science, specifically towards human behaviors. And I'm very interested in both how human behaviors drive public health outcomes. So during the pandemic, that's a very obvious example of that. So for example, like COVID spreads over contact between people. So if people go out a lot, if people are mixing a lot, if they're not wearing masks, if they're not getting vaccinated, all of that is going to contribute to the spread of the infectious disease. So I'm interested in how public health outcomes arise from behaviors, but then also on the policy side, how can we then inform policy and estimate the effects of policies on human behaviors? Because that's another very complex thing where, for example, if a policy comes down, people might react to it, but there might also be spillover effects. So we have, for example, one paper where we're studying spillover effects between counties, where when one county decided to shut down, if the neighboring counties were still open, then people would actually physically cross over county lines so that they could still like eat out at restaurants or still go to the gym. And so policy making during the pandemic, especially over human behaviors, is very complex. It's sort of like trying to like you close one thing and then people figure out another loophole to do something else. And so I'm really interested also in how behaviors complicate and inform policymaking.
Coming up next, the final chapter in our series on AI and public health. Dr. Serina Chang remains with us to share some practical examples of how AI can be used to understand human behavior at scale. You won't want to miss how she walks us through a very cool example of how computer science has unlocked novel data sources, which reveals a new understanding of disease spread in neighborhoods. That's next time on the Public Health Insight Podcast. This show was edited by me, Gordon Thane, with additional editing from LaShawn Benedict. Sound design and mixing by myself and LaShawn Benedict. The original music from The Music Room, composed by Tom Fox, licensed from Johnny Harris. The cover art design for our show by LaShawn Benedict. The Public Health Insight Podcast is produced by PHI Media. Thank you for listening to the Public Health Insight Podcast, your go-to space for informative conversations, inspiring community action. If you enjoy our podcast, be sure to subscribe and leave us a rating on Apple Podcasts or Spotify. See you in the next one.